Welcome. This is the week number 6, that is the module 6, and I will start from today the steel making. So far we have discussed about the blast furnace iron making, all details. I will start the steel making, and before I start the steel making, I will just give a brief history of the steel making. Okay. What I will discuss basically the wrought iron, that is the very primitive iron is the wrought iron, and then I will talk about the evolution of the cast iron, and finally the steel, and also I will talk about the modern steel making, evolution of the modern steel making process. So wrought iron, there is the earliest sample of the wrought iron is obtained in the British Museum. In the British Museum we can find it is around date back to 3000 BC before Christ. And what is wrought iron? Wrought iron is basically solid state, that is the iron that is produced in the solid state. Okay, that is if you just heat an iron ore in presence of carbon, then you can have you can take out the oxygen, that is just like what you call it DRI today, but that time it was much more primitive, and in fact they invented iron. Possibly there is the story goes like that they are preparing some animal food in a outside oven, that is that they used to eat by basically baking the things. So they were baking some mice, and at that time in the adjacent side they have obtained some hard material that is called the iron. Possibly iron stone was there, iron ore was there, and the carbonaceous material they used to burn the things. So in presence of carbon they produce the iron. That is the story goes. So that is the solid state reduction, and then followed by squeezing of the slag by hammering. Basically iron ore contain a lot of gangs. So if you heat up at certain temperatures, say at little high temperature, you can reduce above 1000 degrees centigrade, and that you can do by burning the coal even in the presence of cold air, and then you can produce above 1000 degrees centigrade, and then you can directly reduce the iron ore. What happens is that since you cannot go to the liquid state because it requires much higher temperature, and at that time those temperature was not available. Basically the oven used to run by cold air blast by natural draft, that is to go, and then carbonaceous material basically was there, and that will burn it, and then temperature may be 1100 degrees centigrade that you can attain maximum. So the material will remain solid, and what will happen is that you can take out the oxygen from the ore, you can make it iron, but at the same time the gangue will be there along with it, maybe in the semi-solid state, because some of the slag constituents may form the eutectic and they will be in the semi-solid state at 1100 degree centigrade. So then what you have to do, if you hammer the material, then the slag will be squeezed out, and partially some of the slag will be intermixed with the iron produced. Okay, that is called the wrought iron. So why the wrought has come basically from working. Basically if you work on it, that is called, from that it has come basically wrought iron. Okay, solid state reduction followed by squeezing of slag by hammering, that is called the wrought iron. Now it is produced in the bloomery, basically short cylindrical furnace, and operated with the natural draft, as I said, and you can find a picture of it. So you can find this is the hole, and the air goes through it by natural draft, and they made some cylindrical, cylindrical furnace, and made of stone, and then inside they used to put the iron ore, coal, whatever it may be, and then by natural draft air used to go, and they used to cook for a long time, overnight say, and the morning they get some kind of metallized iron. That is they can get some the iron ore could be reduced and form a metallized iron, and then they can take out that iron, and then they used to hammer it. If you hammer it, after that you can squeeze out most of the slag, but some of the slag obviously will be intermixed with the iron, and that is called the wrought iron, and it has some very special quality. And the iron pillar that is exist in Delhi, that is made of this wrought iron only, and the inscription on the iron pillar says that it is made in the Chandragupta II made that, and his name is written there, some in their alphabets, old alphabets, and it is around 400 after Christ, okay, 400 years after Christ, early 400, there is a Maurya dynasty that time. So, and then you can find this is the iron ore in the Delhi, and its diameter is around 40 centimeter, height around 7 meter, and estimated weight around 6 tons. Okay, this is the, you can, by density you can do that thing. So, and this iron, the most marvelous thing is that about this, very fascinating thing about it is staying for more than 1500 years, but you cannot find any rusting. That is the most interesting thing. Excellent corrosion resistance, and it is because a lot of research has gone, basically some, and then they found there is a protective layer, a very passive protective layer over the surface that basically restrict it from the atmospheric oxidation. And it may be due to the processing, the art of processing, and they find that the three factors, that is the processing, structure and the composition of the iron. Okay. So, as a result, this intermixed slag basically gives this protective layer. They form some passive oxide layer outside and then never allowed any penetration of the oxygen inside it. So, as a result, not only oxygen, moisture, anything cannot penetrate inside it because of this passive layer formation, and it is attributed to the processing, structure and composition. As I said, it is an intermixed with the slag, that may be one the reason, and then that iron contains a lot of phosphorus. So, some hydrated phosphate, something they have found on the wall that basically restricts from this oxidation. So, this is about the wrought iron. This is the very primitive, you can consider it as a steel also, because the wrought iron carbon diffusion will be very less. So, in fact, it is almost a pure iron intermixed with the slag, and carbon percentage will be very less, because in solid state reduction iron carbon do not penetrate too much. So, it is very malleable from that point of view, and then that is the thing. So, this is the wrought iron, and it is before Christ, okay. And then let us see the cast iron. Why? What does this mean? Cast iron means basically you have to make now the liquid iron, and then you can cast it into a different shape, that is called the cast iron. And if you see the cast iron was first produced even before the Christian era in China, and in the Chinese museum you can get some big objects of this, the cast iron, date back to 1000 AD, 1000 AD after Christ. So, those things are there in China. And next significant development, that is after and then this technology basically moved towards the Europe, and next significant development in the Spanish province of Catalonia, that is called the Catalan forge. And what is the characteristic or unique thing is that they use the water wheels to blow the air. So, now so far they used to produce under natural draft. Obviously, natural draft was very smooth, that is the flow of velocity of the air will be less, or partial pressure of oxygen will be less. But if you can use water wheels, obviously you can give air at a much faster rate. So, partial pressure of oxygen will also be high, that is the more blast rate is increasing. So, partial pressure is high, so you can attain little higher temperature also, because the reaction kinetics will be faster, and you can attain little higher temperature, and at that temperature it was possible to melt the iron, carbonized iron I will say. It is not the pure iron, but carbonized iron, which melt around 1200 degrees centigrade. So, that temperature was possible by the water wheels to blow the air, and they used to produce around per 12 hours 100 kg per 12 hours. So, it is significantly increased. And then came the Stukofen, okay, in Germany. That Stukofen furnace, that is the height increased by 5 meter, and interior superior refractory lining was there to restrict the heat loss to the atmosphere. So, they made that, and its shape is more or less like a modern blast furnace, and so it is called the forerunner of the modern blast furnace, and it used to produce 100 to 150 tons per annum. So, quite large amount at that time. And then so far all this furnace used to run by the charcoal, wood charcoal, and then it was replaced by the coke in Dudley in 1709. This is the early 18th century. So, in UK, so this is a great innovation, that is the charcoal is replaced by coke. Obviously, in that case you can increase the height of the furnace, because coke is more stronger compared to the charcoal. Charcoal cannot bear much of much of overburden, so it fragment and produce dust, but coke will not. As a result, with the introduction of the coke, you can increase the furnace height and also the productivity. And then came the steam engine for blowing the air. Now, if you have an engine, then there is a forced convection. Now you are giving the water wheel did not have so much of power. So when you introduce a steam engine, it has much more power. So you can deliver much more air per unit. That is the per ton of iron. So blast rate you can increase by that time. So steam engine air blowing introduced 1760 and increase the size and productivity of the furnace. So you can increase the size and productivity because you can supply more air now. Blast rate can be increased. You can burn more amount of carbon also per unit time. Okay, so productivity increased. Then came the preheating of the air blast in 1829 by the Nansen, and this is very interesting because if you can preheat the air, then obviously you can supply a lot of sensible heat through the air and you can supplement some of the heat supplied by the coke, and so as a result your coke rate decreased. So coke rate decreased from 8 ton to 5 ton. So that was the initial thing, and then further modification increased, that is the by preheating temperature from 150 to 600 degrees centigrade, and the fire brick linings, regenerative Cooper stove, that is the Cooper stove for preheating the air blast, came in 1857. That is in the 19th century, mid 19th century. That is, you get the Cooper stove. That is the modern stove, but with a much higher preheat temperature. Now you can attain 1200. That time 600 degrees centigrade you can attain by that Cooper stove. So it increased the preheating temperature and reduced the coke rate. And then came double bell charging in 1880. Double bell charging, there is a charging system. We understood the importance of the charging system. Otherwise, it was polluting the atmosphere because where you are charging, the gas can escape through that. So a lot of pollution will be there. So once comes the double bell charging, you can restrict the gas leakage through the charging. So that was, so pollution point of view, it was very good. Also the burden distribution point of view also. And then gas cleaning, that is the electrostatic precipitator, when it comes, then gas cleaning become more effective. And then utilization of the blast furnace gas for the gas heating, that is the Cooper stove, as well as downstream application came. And further development we have discussed already, the modern blast furnace development, how the coke rate decreased over the time I have already discussed. So this is the primitive, that is how the cast iron evolved over the time. That is so it was there actually, started from pre-Christian era, that is the BC. It started, the cast iron was started in China, and then progressively it moves to the Europe, and then a lot of development take place on the cast iron. So rest of the development in modern blast furnace I have already discussed. Now I'll go about the steel, how the steel developed. Basically, first is the cementation. As I said, that is the wrought iron is basically a very pure form of iron, okay, and with a very low percentage of carbon. And also I said that is the pure iron is very malleable, it is very ductile, but strength is not that much. So if you increase the strength, if you give some amount of carbon, some impurities into it, then strength increases, and increases, as you know, as a physical metallurgist, because of a lot of strengthening mechanism come into picture, solution hardening and precipitation hardening, dislocation by love, all these things are there. So you know, a lot of strengthening mechanism come in when carbon goes into this system. Now too much carbon, again, not good, because it makes the iron very brittle. So up to 2% carbon you can have different kinds of steel, mild steel, medium carbon steel and high carbon steel, and those are malleable still and with a high strength. So there is the wrought iron was also very that is the strength was not very high because the carbon percentage was very less. So people felt to increase its hardness. So then what is that? There is the heating the wrought iron in presence of carbon in stone box, that is called the cementation process. What you can do, you can increase the carbon into the wrought iron. That was the thing. But if you do that, is the carbon will increase in the surface area only, because the penetration to the center will take a lot of time. So that was not possible. So this type of wrought iron, cemented wrought iron, was very hard on the surface but very ductile inside it. Core remained very ductile, and the surface become hard. Okay, so that was called the steel. So it is a reverse steel making. First you produce a pure iron and then you incorporate the carbon into it. Unlike today, what we do, we produce a hot metal liquid iron with lot amount of carbon, and then we purify it to reduce the carbon to the level where the strength and ductility is optimum, right? That is called the steel. But here first they produce the wrought iron because of temperature limitation, wrought iron, and then they introduce the carbon and then produce the steel. So it is reverse way of making the steel. So cementation, and then wood steel, that is wood steel was available in India in Tamil Nadu area, and this wood word has come basically from the word ukku in Tamil, called the fire. So wood steel, it was a very famous steel and it was the most advanced material during that period. In 200 to 300 BC it was in India. Even after ready up to actually a lot of time, around 1000 years after that also, wood steel was only the advanced material in the world, and it was a fantastic quality it has with a strength and ductility. The wood steel is basically a carbonized wrought iron only, and possibly they produce the way the processing and all these things detail is not known, but major thing is that they take the wrought iron, first produce wrought iron and then carbonized it. But the steel has a very good quality, and this steel, there is the famous Damascus sword was made of in the Middle East, was made from the wood steel, because wood steel was only the very high quality steel at this time, and it is exported to different areas, okay, including this Middle East, and where they produce the Damascus steel with this. In producing it, they hammered the wood steel, maybe the number of pieces of the wood steel was hammered to form some kind of ingot, and then hammering to produce the sword, and then heat treatment of the sword was very important. There is special heat treatment, quenching, air quenching, normalizing, whatever it may be. And then the sword that was obtained is a fantastic quality. And today now it is known that it is an alternate bands of cementite in the matrix of temper, martensite or pearlite, that is the structure. So, and it has a very high carbon steel with a excellent plasticity. Possibly the high carbon only limited on the surface, so surface become very high, hard, that is required for the sword, but the center was very ductile, so you can hammer it easily. So it was hammered and moved away. So all these things basically give a very excellent. This is the Damascus steel, texture of the Damascus steel. It looks like this. So, and then after this wood steel, this era, basically wrought iron and cementation, this is area we came the first liquid steel making, because liquid steel making requires a very high temperature, because that was first Huntsman in UK 1740. He could make the steel in the crucible, obviously the carbonized steel. So with the chemical fuel, with the cold air and the chemical fuel burnt, and then whatever the temperature, around 1400 degrees centigrade, but by that temperature you can melt a high carbon, that is the carbonized wrought iron. So he was the first person who melted the carbonized wrought iron and to homogenize the mixture with the carbon, right? So that was the thing. So this is called the crucible. He could make in the crucible in a very small scale. And in the large tonnage scale, first steel making came in the Bessemer process in 1860. I will talk about that thing. And then alloy steel is a very recent phenomenon, is maybe 100 years old. It is the early 20th century, there is the alloy steel came. And so modern steel making, I will talk about some modern steel making. So to start with, let us talk about the Bessemer. There is the Henry Bessemer. He invented this technique in 1860. Okay, so what is that? Basically, this is the first economic tonnage liquid steel production from the molten pig iron. That is the 152. 10 to 50 tons. Basically, that time lot of, basically you see by that time, that is the cast iron was, people were making the cast iron in the stoke oven, lot of liquid iron was being formed, and these were cast. But so several places the liquid iron was there. So Bessemer wanted to convert those liquid iron to steel, that is to purify the liquid iron, okay, to take out the impurities, okay, by oxidation. So that was the first that time, and it was needed at that time, iron purification by purging of air into the melt. So this, the furnace will show this is the autogenous process, because autogenous process, because you are purifying the liquid iron by oxygen, you are oxidizing the impurities like carbon, silicon, manganese, and as a result you are generating a lot of heat, because all these oxidation reactions are exothermic. So it was an autogenous process, no external heat supply was required, but it was just sufficient to purify the hot metal. So you cannot use any extra cold material, that is the scrap you want to melt into the base iron, not possible, because it was just sufficient to convert a liquid iron to the steel. Okay, so it was autogenous that way, and then process modified by the Thomas for basic steel making, and no cold charge acceptance, as I said. And this is the furnace look like. This is the furnace. It is very much to the modern basic oxygen furnace. Only thing is that here the oxygen in the form of air was introduced from the bottom of the furnace. You can find a lot of holes are there through which the air was passed, and as the air goes, and then oxygen in the air react with the impurities and oxidize them, and carbon monoxide, carbon get oxidized to carbon monoxide, goes away to the atmosphere, and the other silica, manganese, phosphorus were oxidized and collected into the slag. But initially the phosphorus removal was not possible for the own reason, you know, you cannot remove the phosphorus preferentially without you make the slag basic. That's why that is the Thomas modified this process for the basic steel making. Basically make the lining basic and also use lime such that you can reduce the phosphorus content significantly, right. So before that, before base iron process was an acid process. It is called the acid because the slag is acidic, and there you can only remove the carbon, silicon, manganese, not phosphorus. So when Thomas modified this process with the basic lining and limey slag, then he could remove the phosphorus also. So it was a perfect refining unit was there, unit was established. And then the major drawback of this process was high nitrogen, because you are charging air, not oxygen, as we do today. So it was charging the air. Air contains 79 by volume percent nitrogen. So that nitrogen dissolve into the liquid steel to great extent, because obviously because the air bubble moves and the bath was not very deep, so shallow bath. So oxygen residence time was, air residence time was not very high. But by that time, obviously, a lot of nitrogen also goes into the steel. So nitrogen content was around 200 ppm. So it is quite high, 200 ppm, very high, and nitrogen makes very brittleness into the steel. And nozzle maintenance was another problem. The maintenance of the nozzles was another problem, because from the bottom you charge the air, so there is always chance of flooding the nozzle by the liquid head. So later on, the nozzle Thomas also shifted this nozzle to the side, such the nozzle problem decreases significantly. But this furnace has limitation of no cold charge acceptance as well as high nitrogen content of the liquid steel. So that's why they went for some time, but they are not sustainable. But this is the forerunner, I will say, this is the forerunner of the modern LD furnace, because only change is that you are charging now pure oxygen, and that too when the cheap oxygen production came into picture, and then it was shifted to pure oxygen furnace. So now oxygen is lanced from the top in the LD, otherwise reactor look like this. So then came the open heart furnace. Why the open heart? Siemens Martin in 1861 they designed some furnace, that is the chemically, there is the fuel fired furnace that can melt the scrap. That was the needed at that time, because you are generating the steel by Bessemer process, that is the scrap, and then a lot of scrap was evolving, and then how to utilize those scrap, that was the need. But there was no furnace available to melt those scrap at that time, 1861. So parallelly two furnace basically evolved to melt the scrap. One is called the open hearth furnace, that is fuel fired furnace, and similarly after few times, that is the electric arc furnace also came into picture, that also could melt the scrap. So externally heated furnace was required, and Siemens Martin, both brothers, Siemens brothers and Martin brothers, they developed this process, a process where a fuel-fired furnace with a regenerative principle can melt the cold charge, right? So first externally fuel-fired furnace to attain the steel making temperature by heat regeneration principle. So what is this heat regeneration principle? This is the furnace look like. This is a very shallow furnace you can find. This is the liquid metal and this. And then what happens? Here is a fuel fired furnace. So here is the oil burner is there, and you have the preheated air is coming from here. How it is preheated? I am telling there is a preheated air. Basically you burn the oil by the air, and then the exit gas, when it comes out, this is the exit gas in one cycle. When the exit gas is, here the air is going, okay, the exit gas, suppose here the air is going and you have a oil burner, you are burning this, and then exit gas is coming out. When the exit gas come out, then there is a checker brickworks were there. So checker brickworks, as I say, it is nothing but a brickworks with a lot of surface area, such that your heat exchange become very effective, and then the brick can retain the heat. Okay, so here the air is coming, and then they exchange the heat with the brick, and brick get heated up, and they store the temperature, store the heat, and the air comes out. That then goes to the stack. In the next cycle, what they do basically, when similarly it is heated up now. Now it is already heated up, and the air is going. Air get preheated, and then preheated air comes, burns the oil, and the exit gas come, and then again it hits the brickworks. In the next cycle, what will happen? That is, it will be on the air and it will be on the heating, and the air will go, it will be preheated, and it will be burned at the oil burner, and the exit gas will come, and then it will again preheat this brickwork and then come out. So this is in 2 cycles it runs. So you can, so chemical fuel, that is the Benjamin Huntsman, what he did basically, he burned the chemical fuel but with the cold air. Now what they are doing, they are burning the same chemical fuel but with that is the preheated air. That is the difference. As a result, you can increase the furnace temperature to the steel making temperature. Steel making temperature means basically when you are making the steel from the liquid iron, you are reducing the carbon, so its liquidus goes up, so temperature goes, so furnace temperature required around 1600 degrees centigrade, because 1539 is the pure liquid iron melting temperature. So it little higher for, you should have the gas temperature little higher for the heat transfer. So around 1600 degrees centigrade is required, and that was possible by that time. So with this preheating, so preheated air along with this oil chemical fuel, you can generate a very high temperature in the furnace that is able to melt the scrap. Scrap is also very low carbon iron, so its liquidus is quite high, so you should have a very high temperature. Okay. So first fuel fired furnace to accept 100% steel scrap, that was very much needed at that time, because steel was being produced by Bessemer, so lot of steel scrap was also being produced. So those steel scrap was very much required to be molded by external heating furnace. So iron is used as an, in this furnace, how does it work? Basically use the iron ore as an oxidizing agent, and it is a very shallow bath because heat is transferred only from the top and it goes down it. And also it is a very quiescent bath, that is very, and as a result only when the carbon comes out in the form of bubbles, it generates some mixing or some starting into the bath. Otherwise bath is not very, it's mild bath, that is not start bath that much. Only during the carbon coming out, that is called the carbon boil, then some mixing is there. So that's why the bath is kept shallow only for the heat and mass transfer point of view. And iron ore is used as an oxidizing agent, that is the source of iron. And then but you can produce the clean steel here because no nitrogen is coming, because iron ore you are using directly oxygen source, you are not using the air. So nitrogen was very low, hydrogen was less, and very slow process, around 10 hours, and then you can cook the material as you want. You can cook any kind of alloy steel. Okay, that was possible because you have lot of time, okay, to make any kind of steel. But major problem is the time, that is the time. And later on the open earth furnace, not only for the scrap melting, later on when it was developed later stage, it was handling the liquid iron also. Liquid iron contains lot of that is the impurities. As a result, the slag volume in the furnace was also increasing, and it was very difficult to handle a large amount of the slag volume. That's why they make some port here at the top that is called the flash point. When the slag exceed that point, then it will automatically flash off from the furnace. As a result, the liquid height will remain constant, the slag height will remain constant. So that is the flash slag technique was introduced when they were in business of treating the liquid metal also, because it was this open earth furnace was also connected to the integrated steel plant for some time, and there it was handling both the scrap as well as the liquid iron. So then it was converted to twin hearth furnace. That is, the furnace was divided into two parts, one part, two parts, and one part was on preheating, another part was on the melting. Preheating means when the exit gas is coming out, a part of the gas is used up for preheating, and obviously the whatever the sensibility is available, that was sufficient to preheat this checker works. So to shorten the time period, so you can in one half you can preheat it, so you can, and the other part you can melt it. So to shorten the time, this twin hearth furnace also came. Flash slag practice was there, but anyway, this furnace could not compete once the LD furnace took up. So but LD furnace came around 1950, and this is around 1861. So 100 years open earth furnace also served the purpose of making the steel to great extent. Okay. But because of a very long time, 10 hours time, and later on it was reduced to 6 hours, but still it was quite large time requirement for refining the steel. So oxygen, this is the basic oxygen furnace, and this is the oxygen first came into picture when the cheap oxygen produced by Linde-Frankel process give birth basically to the BF process, because Linde-Frankel process bring the very cheap oxygen. From here they could separate the oxygen in a cheap way. So technology was such that is you can produce a cheap oxygen production. So cheap oxygen production by Linde-Frankel basically give birth to the BF process. And oxygen lancing, obviously since oxygen is there, oxygen lancing was done from the top in this furnace, and tap to tap time was only 45 minutes, because here the refining characteristic is different. Since the oxygen come from the trough and the emulsion is formed in the above the slag layer. Okay, emulsion basically first foam formation take place, slag foam, and in the slag foam lot of metal droplet joins, and that forms an emulsion, and basically the refining of liquid metal take place into the emulsion only, where the surface area is tremendous, and that is the, I will talk about that. That's why it is only 45 minutes. So this is, you can see the furnace look like almost decimal furnace, only it is rounded here to facilitate the mass transfer, and you can find this oxygen lancing is there, and this is the emulsion, where basically the surface area is slag metal surface area is tremendous. You can carry out the refining very short time. So from 10 hours or maybe 6 hours, so it is 45 minutes only. And the first pilot plant was set up in Linz and Donauwich in 2 to 5 ton in 1949, that is 1950. So after that, once LD came into picture, then slowly the open hearth phased out because of very large time requirement from productivity point of view. Presently its capacity is 100 to 400 ton. There is the LD furnace is available nowadays. Okay, it is also an autogenous process, not only autogenous because oxygen is coming, but since the partial pressure oxygen is very high here, your basically heat generation is also quite high, so you can accept some amount of cold charge also. And then came the elliptic arc furnace. I said the elliptic arc furnace was introduced. There is two type of elliptic steel making there. One is based on the elliptic arc, and heat source is elliptic arc, as you can understand. And first successful commercial application was by Herold in 1899. Okay, so and then suitable for the small industry, 50 to 100 tons it was there, and you can melt the scrap and produce any kind of alloy steel, because it has a lot of flexibility in the refining. I will talk about that flexibility into the input material also. You can take any proportion of the hot metal if required, because if you want to take this furnace in integrated steel plant also, it is possible nowadays, and you can take any kind of raw metal mix, and bigger EAF for integrated steel plant is also 150 to 300 ton. Now it is also coming. Okay, induction furnace, as the name suggests, basically heat is generation by the eddy current dissipation into the hot metal. So eddy current is generated into the hot metal, and then or the scrap or whatever the metal you are giving, that is the scrap you are giving. So eddy current will be generated, and that will melt the that is those scrap, and it has a very good mixing. I'll come about that thing, and then refining is limited. I'll talk about that thing. So this is the thing, that is your induction furnace was there. So here basically heat source of heat, basically eddy current dissipation into the charged material, and that basically melt it, and finally refining also take place to some extent, but it is mainly for the scrap melting and limited refining. So this is the elliptic arc steel making. There is two is, one is the elliptic arc furnace and is the induction furnace. And okay, so this is the reference, mostly strategy and conclusion. There is the wrought iron and carbonized wrought iron were excellent steel in the ancient time with superior quality. Combined effect of processing, structure and composition of the iron is supposed to be, that is the responsible for very excellent quality of those steels at those time. That is very corrosion resistance, and then the wood steel, those are the. And modern liquid steel making evolved through the Bessemer to open heart to basic oxygen steel making and elliptic arc steel making also. The electric steel making are suitable for small industry to convert the scrap to a liquid steel, basically scrap to steel. Nowadays, they are also making inroads to the integrated steel making, as I said, because now bigger electric arc furnace is coming, and they have a flexibility in the raw material. They can take any proportion of liquid steel with the cold charges. That is the most advantage. And cold charges are scrap. It can be the DRI nowadays. So this is a very brief history, and thank you very much.